Hi folks, this is day 10. We're starting proof by contradiction today. Let's go ahead and get started. A proof by contradiction is a verbal implementation of this argument form. Here, C stands for any contradiction, as opposed to a tautology, a statement that is structurally false. If we assume that the negation of P is true, in other words, if we assume that P is false, then that leads to a contradiction. Then it must be the case we can conclude that P has to be true. That's the idea. We're going to assume that P is false, show that that assumption leads to a contradiction, and then conclude that therefore P is true. Okay? This proof is well suited for showing an upper bound or lower bound on the size of a set. That's kind of the thing that contradiction proofs are good for. If we want to show that something does not exist at all, in other words, the size of the set of these things is 0, then the upper bound is 0, the lower bound is 0. We can show that it doesn't exist by assuming that it does and showing that its existence leads to a contradiction. We can prove that something exists and is unique. Unique means that there's just one of this item. And so we assume that there are two of the item and show that having two of them creates a contradiction. By going above the bound on the size of the set, showing that going above that bound creates a contradiction. We can use it to prove that a set is infinite by going below that bound, supposing that we only had a finite number of these objects, and showing that there's something that we can't do, something that's impossible with only a finite number of these objects. And if we can show that there's a contradiction with only a finite number of objects, then the size of the set has to be infinite. So that's going to be the way we're going to do proof by contradiction. We've got some examples on deck. Let's go ahead and start on one of them. Okay? So we want to prove that there is no integer which is both even and odd. Okay? This seems silly, it seems obvious, but I want to start with a very simple example. Okay? So what we're going to do is we're going to assume that there is an integer that's both even and odd, and then we are going to show that it leads to a contradiction. Okay? That's the idea. So, we tend to let the reader know that what we're arguing is sort of an argument based on nonsense. We're doing a contradiction argument, which means we are assuming something false to show that that false assumption leads to a contradiction. And so we sometimes say we are going to prove this by contradiction, or the following is a proof by contradiction, or assume in order to reach a contradiction that. There are a couple of ways we want to do this. But the first thing we want to do is let the reader know this is a proof by contradiction. You can do this by saying, you can literally just say, this is a proof by contradiction. Okay? And that's literally all you have to say. There are fancier ways of saying that. And then we have to assume the negation of what we're proving. Of P. So in this case, we're going to assume there is an integer which is both even and odd. Okay. All right. If you want to combine steps 1 and 2, one way we can do this is to write says assume in order to reach a contradiction. In other words, we're letting the reader know that the reason we're assuming this is to reach a contradiction. That there is an integer. Let's go ahead and give it a name. There is an integer x, which is both even and odd. All right. Okay, so now that we have our assumption, we're going to apply any definitions we can to that assumption. Since x is even, there is an integer I'll call it j, such that x is equal to 2j. And since x is odd, there is an integer k such that x is equal to 2k plus 1. Okay, so we've applied the definitions. This is what it means to be even, and this is what it means to be odd. Then we're going to do whatever kinds of calculations or work it needs to take to reach a contradiction. Show a contradiction. Well, since both of these equal x, therefore 2j equals 2k plus 1, or if I bring this around, 2j minus 2k is equal to 1. I'll say, instead of or, I'll say so. So j minus k is equal to 1/2. Divide everything by 2. By the closure axiom, j minus k is an integer. But 1/2 is not an integer. Do you see the contradiction? I have two things that are equal, but one's an integer and one is not an integer. Therefore, j minus k equals 1/2 is a contradiction. Okay, so now that we have the contradiction, then we can conclude that the original statement must be true. Okay, the argument form was that if the negation of P led to a contradiction, then the conclusion is that P itself must be true. And so we can conclude that there is no integer which is both even and odd. Therefore, there is no integer which is both even and odd. Okay? Let the reader know that this assumption you're making, you're not crazy, you're assuming it for a reason. So let the reader know that this assumption is in order to reach a contradiction, that you're going to prove something by contradiction. You can combine statements 1 and 2 the way we did here. Apply the definitions, in this case, what it means to be odd and even, to the integer x, so that we have something that we can calculate with. And then we can work through those calculations to show a contradiction. And once we have shown that contradiction, then we're finished with a premise. We then get to show the conclusion. Therefore, there is no integer which is both even and odd. Okay? All right, so let's keep going with another example. Okay? One of the integer axioms, we saw these some time back, and we've talked a lot about the closure axiom. But we have an axiom that says that there is an identity element 0, so that a plus 0 is equal to a for all a equals z and z. What we want to prove is that that identity element is unique. In other words, that there is only one such identity element. Okay? So how are we going to prove this that's unique? We're going to assume that it's not unique. Okay? That there's more than one of them. And then show that it leads to a contradiction. So this is a proof by contradiction. So we're letting the readers know that the assumption that we're about to make isn't, we're not serious about the assumption. We know that it's false. We know that it can't happen, but we're using this assumption to make this proof. Assume the identity element is not unique. Okay, so now we're going to apply some definitions, and here's the definition. That is, there is an integer, an element 0, such that a plus 0 equals a for all a in the integers. And there's another element so what do we want to call this other element? We can't call it 0 because we've already used that number. This other element can't really exist. So I'll call it star, such that a plus star equals a for all a in the integers. Okay? So we're assuming that we have these two elements. 0 that works the way that 0 always does, and star that works the same way. Okay? So now we have to do some contradictions. So we let the reader know that this is a proof by contradiction. We stated what we are assuming. The reader is not surprised now that we're making this crazy assumption because we're letting them know. We know this is a crazy assumption. We're going to prove that it can't happen. And then we apply the definitions of what an identity element means to get two different identity elements. And now we have to do some calculations to reach a contradiction. Okay? So here's the calculations. Since 0 is an identity element, star plus 0 equals star. Because we add 0, anything plus 0 is itself. But since star is an identity element, zero plus star equals 0. But we have another axiom called the commutative property. by the commutative property 0 plus star equals star plus 0. And so 0 equals star. This is what 0 plus star is, and this is what star plus 0 is, and they're equal to each other. But this is a contradiction because we assumed that this was not unique. But 0 and star are different elements. And so 0 equals star is a contradiction. Because we were assuming that they were not unique. We're assuming that the identity element was unique and that star was another element, not the same element. So they can't be equal. Well, now that we have a contradiction, then the original statement is true. Therefore, the identity element is unique. All right. So we're finishing finally with our conclusion. It sometimes takes a little bit of work to build up to that contradiction. That all of this is building up to that contradiction. But once we have that contradiction, then we can make the conclusion that the original statement has to be true. So that's how a proof by contradiction works. We make an assumption that sounds crazy, that the thing we're trying to prove, we're going to assume that it's false. But then we work our way from that assumption to a contradiction, that two things are equal that can't be equal, or two things, one is greater than the other and one is less than the other, or something that can't happen. And once we have that contradiction, then we can conclude that the original statement had to be true. All right. Let's try one more. This is going to involve prime numbers. I think most of you already know what a prime number is, but let's go through the definition. A number is prime if it is an integer greater than 1, and its only positive integer factors are 1 in itself. So, for example, 7 is prime because 7 only factors into 1 times 7, but it doesn't factor into anything smaller than that. 8 is not prime because 8 can be factored into 4 times 2. And so it has factors that are not just 1 in itself. We have a theorem, and we're not going to prove this theorem in this class. If you are interested in seeing the theorem, we prove it in 3124, but we don't prove it in this class. But every positive integer greater than 1 has a prime factorization. For example, 14 factors into the prime numbers 7 and 2. And we can write the order factors in a different order, but the order is, except for the ordering, the factorization is unique. There's no other way to break 14 up into prime factors. 20 is 2 times 2 times 5. And again, I can write that in a different order. But there's no other way of breaking up 20. It's 2 and 2 and 5 in some order. So if every positive integer has a prime factorization, and except for the ordering, that's unique. We're going to use that theorem in this last statement, okay? All right, example 3. We want to prove that the set of prime numbers is infinite. Okay? So the idea is we're going to assume that there are only a finite number of prime numbers, and then show that that leads to a contradiction. Okay, so here's our proof. We're going to say it's a proof by contradiction. All right, so we've let the readers know what to expect. And now here's our crazy assumption. Assume the set of prime numbers is finite. Okay, now let's apply our definition. What does it mean to be finite? Then the set, let's call it capital P, the set P of prime numbers, then P is equal to P1, P2 up through Pn for some integer enter. There are only n primes. N may be a very large number, but it's a finite number. Okay? So now that we have applied our definition, we have to do some kind of calculation that leads to a contradiction. And the calculation we're going to do is we're going to let K be the product of all of these prime numbers plus 1. Okay? So what is true about K? K is not divisible by P1 because it has 1 left over. It's a multiple of P1 plus 1 left over. K is a multiple of P2 plus 1 left over. K is a multiple of P3 plus 1 left over, and so on and so forth. K is not divisible by P1 or P2 or P3 or Pn. Therefore, the prime factorization of K contains a prime number that's not in P. It doesn't contain any of these prime numbers, and so it must contain a number that's not in P. But P was the set of all the prime numbers. Then the set of all prime numbers does not contain all prime numbers. Does not contain all prime numbers. Well, that sounds like a contradiction to me. That is a contradiction. And so the set of prime numbers is infinite. Okay. All right. So we'll look at a few more examples next time of proofs by contradiction, but we want to move on and talk about proof by cases. So take care. See you Wednesday.